Hello everyone, this video is about arithmetical op amp and how it has been designed. Let us see what is operational amplifier. It is a basic amplifier that amplifies the given input signal. So on those days before this computer were existed, by using operational amplifier they used to calculate addition, subtraction, multiplication, division. Have anyone of you wondered how these calculators are been calculating? No one knows until we come to know about this operational amplifier. So this is being constructed by using simple components like resistors, capacitors. So it will be very easy to understand. So first let us see operational amplifier. This is the basic circuit diagram of an ideal operational amplifier. It contains two input. One is non-inverting, that is connected to the positive side, and inverting terminal, that is connected to the negative side. And it contains only single output, that is V out. And this op amp can or have the potential to transform the given input signal to 1 million times greater than the given input signal. And the gain in this operational amplifier is the given here. V out is equals to gain in the operational amplifier and the difference between the two input terminal. There are two types of or two ways you can use an operational amplifier. One is closed loop and the open loop. In closed loop, there will be a feedback feed into the negative terminal of the op amp, which is named as negative feedback. And now let us see the characteristics of the operational amplifier. So there are two types of op amp, ideal op amp and equivalent op amp. So in ideal op amp, the input impedance, that is Rin, is infinity, whereas in equivalent op amp, the input impedance will have finite value about in mega ohms, and the voltage gain AOL is infinite in ideal op amp, whereas in equivalent op amp it has a finite voltage gain. And the ideal op amp have the offset voltage is 0, that is offset voltage is nothing but when the feedback is connected to the negative terminal, all the current entering to the negative terminal is 0 and it fed back and it is been supplied to the feedback terminal. Whereas in equivalent op amp, there will be a slighter offset voltage. The output impedance R out will be 0 for an ideal op amp, whereas there will be some few ohms in the equivalent op amp. The CMRR, common mode rejection ratio, is infinite in ideal op amp and finite in equivalent op amp. Op amp for arithmetical operation. Using this op amp, we can build a basic arithmetic calculators like adder, subtractor, differentiator, integrator, log, and antilog. Adder, a circuit that produces an output which is equal to the sum of applied inputs. Let me show you. So take a look at this circuit. There is a 2 voltage given to the negative terminal. At this output V out, we will get the value of V out will be the addition of this both V1 and V2. So that is that the input is given to the non-inverting terminal and the other terminal is grounded using virtual short concept. That is, when this terminal is 0, by using virtual concept, this point also will be 0 according to virtual concept. Now let us see how this has been derived. Using nodal equation or Kirchhoff law, the current entering in the the current in V1 R1 and V2 R2 will be the sum of current entering to the RF. That is, V1 by R1 plus V2 by R2 is equals to minus V0 by RF. And at last we get V0 equal to minus RF V1 by R1 plus V2 by R2. When the resistance are equal, we get V0 equal to minus V1 plus V2. That is the sum of both the voltages. The negative sign indicates that this is 180-degree phase difference between the input and the output. Second, subtractor. It is the difference of the applied input. That is the difference between the voltage applied between the inverting and the non-inverting input. The given below diagram has both the terminal has some voltages. That is, the negative terminal as V2 and the positive terminal as V1. So at this V out, the difference between these two voltages are been get by this value. So let us see how it has been derived. As same way, it has been derived using 3 steps. 1. By grounding V2, we can find V1. That is, using voltage division principle. That is, Vp is equals to V1 R3 by R2 plus R3. This point is Vp. So after finding Vp, V01, that is output of the V1 circuit. That is, this circuit V01 is equals to, when voltage V1 is applied, Vp 1 plus R by Rf by R1. That is this feedback resistance. So V0 equal to V1 into R3 by R2 plus R3 into 1 plus Rf by R1. And second step is opposite of this. The V1 is grounded and V2 is given. In this same manner. So we get V02, the output V02 is equals to minus Rf by R1 into V2. So at the third step, we need to add both V01 and V02 to get V0. So V0 equal to V1 R3 by R2 plus R3, 1 plus Rf by R1 minus V2 by Rf by R1. So when all the resistance have the same value as R, then the output is V1 minus V2. That is the difference between the two input applied voltage. Third, differentiator. Differentiator is a circuit that produces the first derivation of the given input signal. This is the circuit diagram where the capacitance is connected in front and the feedback resistance. The current entering this capacitor is I in and the current entering into the resistance is IF. So using Kirchhoff law, current I1 plus I2 is equals to 0. So I1 is nothing but C D0 V differentiation of voltage by plus V minus V0 by R. We get V0 equal to minus RC dVi by dt. It is in the form of differentiation. So when RC is equals to 1 second, we get V naught equal to minus dVi by dt. Vi is nothing but the voltage input, and the negative sign indicates the 180-degree phase shift between the input and the output signal. Same as we see in the differentiator, integrator also have the same circuit, same operational amplifier circuit, but the capacitor will be given in the feedback and the resistor will be given where the capacitor been placed in the differentiator. So as seen in the differentiator, same using applied Kirchhoff law, we found that dV naught, it is dV naught equal to minus Vi by RC into dt. Applying integration on both sides, we get V out is equals to 1 minus 1 by RC integration of Vi dt, where when RC is equals to 1, V naught equal to minus integration of Vi dt. Same, we can construct logarithmic and anti-logarithmic. Logarithmic and anti-logarithmic can be constructed using diodes and transistor. Now we see the log amplifier using diode. The derivation is the current entering in the IR is equals to ID. As seen in the diagram, the IR entering in the resistor R1 will be the same as the ID entering in the diode, and the V out is nothing but minus the voltage of diode. And after deriving, we get, before deriving, ID is equals to V in by R, that is the ID is equals to voltage input divided by R, and ID is equals to Is e power Vd by phi of Vt minus 1, where Is is equal to reverse saturation current, Vt is equals to thermal voltage, and Vd is equals to forward voltage current, and eta is nothing but the ideal factor that lies between 1 to 2 and depends upon the reverse saturation current. And Vt is equals to K times T by Q, where K is equals to Boltzmann constant and T is the temperature of the diode and Q is the charge of the electron. After finding this, ID by Is equal to V E Vd by phi Vt, eta Vt. Applying log on both sides, after deriving, we get V out is equals to eta Vt log of V in by R into Is, where ID is V in by R and Vd is equals to minus V out. After simplification, we get V out. So as we see in logarithmic, same as we can do anti-logarithmic, that is diode will be given here, and resistance will be opposite to that. So applying the same KCL rule or KVL rule, we can find anti-logarithmic value. So uses of log amp is nothing but using log amp we can find multiplication and division of the signal. Finding root and power of this signal will be more easier way. And you can see in this signal picture, V1 and V2 are given to two log amplifiers, and we get log V1 and log V2. When this been added, we get log V1 and V2. After applying anti-log, we get V1 and into V2 as the output. In same way, we can build a divider using log and anti-log op amp. So this diagram here given is, we can find the power of the signal, and this diagram here we can find the root of the given signal. That is, the applied signal is A, it's been log A, then multiplication, like B is multiplied to log A, we get B log A and goes to the power log A power B, which is now again reverse, like anti-log is applied, we get AB. Same way in root of the given signal. So advantages of op amp. Stability of the input signal is negative feedback of op amp is increased. That is, the stability is being increased when a negative feedback is given.